architecture with, you know, like all the training, like learning rate schedules and things like that, and then kind of just use that over and over. It's really all about the depth. It's really what matters. It's really has very little to do with like the actual like details. I mean, some details matter. It's an art, and it's, you know, but it's all empirical, so there's no proof. It's like this is the one. It's just you get kind of comfortable with like a deep architecture and use it all the time.
So you're saying, kind of just generally speaking, that the depth has a lot more to play.
Yeah. Oh yeah. The depth matters. Oh yeah. We like it deep. Smooth, deep. All right. All right. How is everybody doing? Pretty good? I see one thumbs up. I'll take that as like everybody's a thumbs up. That's what you do as a professor. You just sort of like ask questions you know no one's going to answer, except for like one or two people, and you're like, yeah, good. We're all buddies. All right. Homework due this week, right? How we doing? Raise your hand if you have started the homework. Yes, I think I see some hands not raised. You are in trouble. I am serious. If you have not started the homework, think about dropping this class. I'm serious. I have done this for 5 years. I know what I'm talking about. You either start right now and work on it for 20 hours straight, or think about dropping this class. It is not an easy thing to pick up. So yeah, how's that for a warning? Does that feel like dire enough? That's another trick that professors use. All right, so we're not linked into the right source here. There we go. All right, so we'll continue. Now we're really getting into like deep learning and what you have probably seen and think about as deep learning. Today we're going to start talking about convolutional neural networks and convolutions as an operation. So the way this course is structured, we spent the first 3 weeks really like basics of machine learning, basics of optimization, at least like first order optimization like gradient descent. We've talked a bit about the structure of classification problems, at least some ways of approaching them. And we've talked about loss functions for models that give you scores for a classification task. And we're going to kind of continue with that framework. A lot of the machine learning tasks that we're going to be using to motivate what we're doing is still going to be classification, mainly because it's just simplicity and also just kind of nice pedagogically to just keep using that same thing. We'll eventually talk about other tasks and other types of losses, but what we're going to do now is to get into the architectures for neural networks that have allowed deep learning to really work. And we're going to do this for convolutional networks. So we've also kind of started with not just classification, just generally, but classification on images. And this is convolutional operation, convolutional layers in neural networks is really the key, has been the key for a long time for working with images. It's not totally the case anymore. There are other types of architectures that are not convolutional, or there are actually some convolutional aspects to them, but in general not convolutional. And we're going to be talking about those as well. But so anyways, we're going to do convolutional networks for a little while, kind of build up some understanding and intuition there, and then we're going to get into other types of problems. We'll talk about sequential data, talk about sequential models, we'll talk about transformers. We're going to talk about generative models, both in the sequential and for image data sets. We'll get into reinforcement learning at the very end. So we're going to cover a lot of different things, but we kind of ease our way into it through classification tasks on image data sets and convolutional networks being kind of the primary tool there. So there you go. Convolutions, what does it all mean? Well, a little bit of history here at first. So, once upon a time, there wasn't any neural network or deep learning, and it was the 50s, and everything was in black and white, and you had a guy named Frank Rosenblatt develop kind of the first neural network. It was he called it a perceptron. It sounds really kind of like futuristic, plus it has like kind of perception in there, so it's like, whoa, this sounds really great. And then he embodied the perceptron in this like cool machine that basically could like recognize big, huge poster board numbers. By the input was literally like these were like literally neurons, like input neurons. Each one of these photocells, so like 400 pixels, and basically like you could tell you if there was like within its field of view, like if it was like black or white, like the thing it was looking at was black or white, and so it could kind of like take the input of like say a 4 or a 9 or whatever, and then turn and then through like a fully connected neural network. I mean, it's a little bit different. Like the activation was a little bit different and things like that, but just kind of what we did last time. You had a couple of layers of that, and I could recognize numbers, recognize letters of the alphabet. These big, huge things you put in front of it, and there you go. Like an artificial intelligence was born, and Rosenblatt became very famous for the perceptron. And it's interesting because, like, actually, the idea of artificial intelligence existed way before this. I mean, obviously, people have been thinking about how would you make, automatic systems, automatons, and give them reasoning and such. And there's a whole branch of AI called symbolic AI that still exists today and still important and maybe researching a little bit. But when it comes to like sort of like the beginning of artificial neural networks, this is probably the beginning of it. So 1950s, 1957, Frank Rosenblatt. I don't have it here in the history, but not too long after that, a couple of like famous AI people from that time period wrote a whole book called Perceptrons, actually. So like Frank Rosenblatt, who was the inventor, didn't write the book. It was actually these like symbolic AI people. They wrote a book about perceptrons and basically like literally described what they were, like the the architecture, like the computational ideas, but then spent most of the book saying why they were a terrible idea. So you can buy a book on perceptrons today whose job it is to tell you why you shouldn't use perceptrons. And there was their way of making sure that the symbolic AI agenda was considered the best agenda for AI at that time. So poor Frank Rosenblatt sort of came into prominence and then kind of fell out pretty quickly after that. But then there were some other attempts that were made. Again, in like this this idea of being able to like understand what it is, what's in an image. And maybe like the next kind of attempt at this that had any sort of that maybe you could consider successful for the time was something called a neocognitron. This is from the 80s, 1980 itself, and it actually has a weird architecture. I'm not going to really get into it, but it introduces some of the operations that we still use today in convolutional networks or in neural networks in general, when you have some sort of like kind of spatial arrangement of your data, this idea of pooling. And so it had these different kinds of like cells or like neurons, these different operations, and some of them had connections that were modifiable, kind of how we what we looked at last time with fully connected networks, and then other ones that didn't have these modifiable parameters, but they perform a pooling operation. We'll talk more about pooling, but pooling is a kind of a funny word to say. We take a group of pixels that are arranged near each other, and we replace all of that whole pool of pixels with a single value. It's a way of kind of reducing the dimension of your data so we kind of pool all that together with some operation, averaging max, some, you know, any one of these. I don't know what it does well enough to tell you that. Sorry. Maybe. Then later in the 80s, you have this paper, we've already referenced it. This is the paper on backpropagation with Jeff Hinton, who's become one of the kind of the leading, or recognized as one of the people who really led us into the modern neural network deep learning era. So the algorithm of backpropagation comes out in 1986 in this paper. Backpropagation had been described before. This was a paper that that didn't know about the existing literature. I mean, of course, think about 1986, how you would get your information. I mean, like you went to the library, like you can't go read every single paper there ever was, right? You can't read all the books, and so I can imagine this kind of thing happened a lot, especially if like the areas that you're in, computer science, or when this showed up in some other way. Like I don't know, like you could imagine this kind of thing. Repeated descriptions of the same things over and over, but they get the credit, at least in the modern era, of like making backpropagation useful. So that's good. And then we really get this paper here in 1998, really probably like the first, like what we call a modern convolutional network. Its job was again to recognize characters, so letters, in an alphabet, numbers. And it has like all of the components of a modern convolutional neural network. So it has convolutional operations, and we haven't really talked about them yet, but the idea is that instead of looking at instead of having fully connected layers, we're actually going to have layers that have a filter of a certain size, usually very small compared to the image in terms of number of pixels. Things like 3 by 3, 5 by 5, usually odd numbered sides for this filter, and the operation is to basically do a dot product of the weights within this filter with the input values, and then the output of that, it's a dot product. So you do all these entry-wise multiplications and you add everything together. That becomes an entry in the output, the feature maps as they're often called, and that becomes the input to the next convolutional layer, and so forth. You have ideas of pooling called subsampling here in the original image, and then importantly, a few fully connected layers. And you'll see this for all of modern convolutional networks, except when they're not there. Almost always you'll see that at some point we take the feature maps coming out of like a final convolutional layer, and we sort of stretch them out in some way to make it like a long vector, and have a couple of fully connected layers, and then that eventually goes out some output. So if we're doing classification to scores, one score for each of the classes, and then that would go into appropriate activation like a softmax, which would then go into a loss function like cross entropy. And so 1998, you get really kind of the first modern convolutional network that really sort of worked. Worked for a very simple type of data, but it worked. By the way, super interesting. If you know anything about the people involved in deep learning, you have, along with Jeff Hinton, you have Jan LeCun and Yoshua Bengio, who won. Well, the three of them all won the Turing Award a couple of years ago for their contributions to deep learning. And Leo Buteau is another very prominent deep learning person now. So back in the 90s there were so few people actually working in this, and so many people saying what a waste of time, don't work in that, that it's interesting to kind of see. Now they're all doing these amazing, great things, and these big companies and commanding huge salaries. But these were all just kind of huddled together, saying if we just keep with this, I think we're going to have $10 million salaries one day. So let's just keep doing this. Now, of course, especially Joshua Bengio doesn't even think that way. He's all about the science. He's quite amazing that way. I'm sure the same with Jan LeCun. I just don't know Jan at all. Cool. So then what happens? Well, still haven't. So remember, you know, 2012 is coming, right? Like that's the year when AlexNet, a kind of convolutional network, wins the ImageNet recognition competition. So you have these little tiny convolutional networks that kind of worked on these really simple data sets. How did we get to AlexNet, which is a much larger convolutional network? Well, along the way, Jeff Hinton kept working on neural networks and started to try to do things that would produce greater depth, like more transformations in the representation of the input. And he started working on, I can't remember if he actually defined these or if they existed, and he started to show how you could use them. But these things, it says RBM right here, restricted Boltzmann machines. And the idea is not unsimilar to an autoencoder, kind of a straightforward autoencoder that you might have already heard of and we'll talk about later in this class. But the idea was that you could, these networks that you wanted to do a task, that you could treat these as if they were a kind of statistical model, and then kind of pre-train them layer by layer in such a way that you could get depth, like you could get 4 layers or 5 layers, which was quite deep, and which couldn't be done in the past, and for large large images, not just like simple images of alphabets and letters and things, or numbers and things like that. So so a lot of like innovation at this time in terms of like how one would actually be able to effectively train a deeper network. And then finally in 2012 you get 2 results. The one that becomes very famous is, of course, the 2012 ImageNet classification result that we've talked about a couple different times. And then there's also another one in that year that builds off of work that Jeff Hinton had started, I think while at Microsoft, if I remember right. He was at MSR for a little bit. And it's in speech recognition, so very different application, but there wasn't like a famous competition that he was trying to win, but like on some benchmarks that this team was able to do very, very well, better than any kind of statistical approach that had been taken before, in terms of speech recognition, like recognizing words like from the actual audio. And there are also neural networks very similar to what was done to win the ImageNet competition. So all of a sudden in 2012, people are like, hey, wow, neural networks might actually be a thing, right? And for years, people have been saying, don't waste your time on those, they're never going to work. So give people like Hinton credit for sticking with it for so long and trying to, and making these things work. But yeah, so this is really kind of like, this AlexNet is really like the first deep learning architecture. It's a convolutional network that, like worked really, really, really well. And it's a combination of the architecture and the ways of training on GPUs and how to deal with learning rates and things like that. Questions so far? This is just like history, right? Just gonna get your history credit for the day. One more piece of history. This is called AlexNet, and if you're, I can't remember if I pointed this out when we've seen this before, but if you're like perceptive, something feels really bad about this image, right? And it's the fact that the top of the network seems to be like cut off, right? Like there's like kind of like 2 halves to this thing, and it looks like this is all cut off. And it's true in the actual paper, when they typeset it, they typeset it in such a way that the top of this image just got cut off. So forevermore, the image associated with the first like really modern convolutional network is a total mistake. Like it's missing part of what should have been there. So that's kind of weird. I don't know, just happened. Thank the typesetter. anyways, it's called AlexNet because Alex is the first name of the first author there. Again, so many of the names that show up on these early papers are now doing, amazing things. I think I already pointed out. Alex has sort of left deep learning, if I remember right. He actually had a company for a little while that was doing like facial recognition. I think it got to be too much and like too much controversy or whatever. I think he just kind of dropped it all. I have no idea what he's doing now. And Ilya Sutskever is the chief scientific officer at OpenAI, which is cool. They're doing cool stuff, although they're not open anymore, which is one of the weird things about the history here. It was going to be like AI for the masses, and now it's more like how much money can we make? But yeah. And one more piece of history, I did say this last time, but it's worth saying. These three, from this competition, basically created a company called DNN what? Research, I think is what it's called. It was just them. They had there was no product or anything, and there was basically Jeff Hinton at I think it was at a NeurIPS conference, but one of the big AI conferences, basically held an over email auction with 4 of the big companies at the time. So like Microsoft, Google, DeepMind, which was not at this point hadn't yet been acquired by Google. That didn't happen until 2014. And one more. What was the other one? Can't remember right now. Shoot. Anyways, held this auction where basically has them auctioning, saying like how much would you pay for our company, and eventually stops at 44 million and sells it themselves to Google. So, and they split it 3 ways. That's how cool Jeff is. Jeff could have taken it all, but split it 3 ways. So all these 3 started their lives, well, the 2 started their lives, not Hinton, he was already well advanced in age, but with, a third of $44 million. Not a bad PhD dissertation, if you ask me. I didn't make quite that much when I did my PhD. I think it cost me more than I got. I didn't do it right. Okay. So if you fast forward now a few years from then, common nets were everywhere. They're still in a lot of places, but they were everywhere. You start just doing all kinds of cool stuff with them. Classification. You start to have the search engines now. We're starting to be able to do really cool things with like images and saying, how can we search for images of the same types of things? They were using features from deep learning models. You could do, we're going to look at how to do these kind of, like we're going to talk about these architectures, but you could get, it's not just say like what's in this object, but you can now start to draw bounding boxes around the things and classify what's in there. Multiple objects within an image. You could do this really cool thing called semantic segmentation, where you're basically labeling every single pixel. Like every single pixel gets classified into these coherent, this whole thing's a row, this is a person, so on. Really quickly, right? Like this was already published in, 2012, 2015. Self-driving cars, obviously. People started working on them. I actually have a Tesla that I drive in self-driving mode kind of all the time, mainly because I'm an AI person and I feel kind of like I'm supposed to. And it's also like exciting to feel danger all the time when you're driving. And yeah, I haven't had an accident yet, but I should have probably had a couple. But it works really, really well until it doesn't. I mean, it's really amazing. It's really amazing actually how far they've gotten. But like even last night I got an update to the full self-driving, so I'm like, oh, what kind of craziness happened this time? But I mean, I'm going to show you the architecture here in a second because they showed it to everybody at Tesla AI Day like about a year ago. I have a slide here in just a second, but they're using convolutional networks basically to process all the video from the 6 cameras that Tesla has, and there's no LiDAR, radar, or anything like that. There's no other kind of sensing equipment for the driving. It's all video, which is amazing actually. Yeah, you can do all kinds of cool stuff. I'm probably gotta hurry up. one of the cooler things that's happening, this is kind of old now, but like there's way more modern versions of this. You know, people are using convolutional networks and they're doing science with them. So what's done here is, you know, these are pictures of galaxies, and then they get, basically these get auto-encoded. So they're basically, the idea is that you have this like very high dimensional image, high resolution image, and then you're going to compress it down to a very small vector, at least compared to the size of the image. And then you can use that compressed vector as a representation of it that allows you to do all kind, you know, to like extract information about what is in this, what's this galaxy like, what's in this galaxy, that kind of thing. And like it actually makes for like you know, scanning through the massive amount of data that comes out of, you know, these telescopes, and you know, sort of like automatically, right? So you find this, you know, super helpful. This is actually doing a very similar thing, but now for recognizing tumors. These things are far from perfect. They don't yet, you know, replace trained human doctors and, you know, medical experts and things like that. But, you know, there are massive problems with them. No one should actually accept the diagnosis of a machine learning model yet, without a little skepticism. But they are getting quite good. You know, and maybe at some point, maybe not even too far from now, we'll really have amazing systems that can generalize really well to all kinds of, you know, all kinds of ways one might obtain an image of, say, a tumor, skin tumor or some kind. All kinds of things happening. Yeah, I don't know. I won't spend too much more time. We actually looked at image captioning in the reverse, and you can do really kinds of wild things with convolutional networks, with very much just doing some of the things we talked about last time when you all were asking, like, you know, why would you want to look at the gradient with respect to a pixel? Well, it's a good question, since what we're trying to optimize are the parameters for the task. But if you kind of change the task around, or just kind of let this thing loose and like optimize itself by following gradients, you can get all kinds of weird things to happen, which we'll explore a little bit later in the class and some of the homework, which is kind of fun and helps you get a little bit of a sense of what's actually happening inside of these networks. Like what does it mean to like learn a thing? You know, what kinds of, like, what's the geometry of this as depicted by how it changes the images? And like I was saying, Tesla, for instance, you know, I would argue is, you know, at the forefront of full self-driving autonomous vehicles. They have there are 6 cameras, and each one of these has at its core a trained neural network, a trained convolutional network that has all kinds of cool stuff happen to it, and eventually, you know, becomes the predictions that it's, you know, all the signals it uses to drive, not only to like decide how fast to go or you know, which directions to turn, but, you know, also being aware of dangers around and things like that. And then, anyways, it's amazing how well it works, and it's, you know, at the heart of it, it's the technology that we're going to be learning about over the next couple of weeks. So, pretty cool. It is important to remember that convolutional networks are no longer the only architecture in town when it comes to images. Visual transformers are now real, you know, like people use these a lot for different kinds of projects, and the question of like which one would you choose kind of depends on a lot of factors, and we're gonna you'll at least be introduced to convolutional networks and visual transformers both, and, you know, we'll at that point we'll say more about like why we might choose one over another, like what are the inductive biases of each. And that's really important when thinking about architectures, is like, what does the actual details of the architecture, like, what's it for? You know, what kind of data? And pictures like this we'll see a lot more of as we go through the class, but these are often ways of visualizing like what's being learned in a convolutional layer. So these are filters. Think of these as like, you know, as vectors, and when another vector in an image looks like this, we take dot products, you're going to get a large dot product, you know, a positive product, meaning that these things are like aligned. and that's some signal saying, hey, like you look like a one of these things. And when you start distributing that across, the whole of the image, and then have this kind of idea abstracted through many, many layers, you build up, these visual concepts that allow you to do your tasks. And in a visual transformer, you have something similar. You don't have convolutional filters, but you have some kind of initial filter, and these are what they look like. You can visualize them, and you can see how they're different from these in a lot of ways. They're similar in other ways, and yeah, it's fun to be able to visualize some of these things and think about what is being learned. And again, we're going to spend time figuring out learning ways of kind of how would we ask these questions and how would we get into it. So how would we look at this for our own problems? And of course, Optimus Prime is always with us. Yeah. Okay, so let's finally talk about convolutional networks. So remember fully connected layers. Fully connected layers, you basically have a vector input and you have a vector output, and your model is some parameterization, and so typically what this looks like, right, is that we have a linear function that takes the input, transforms it, and then we have like a nonlinear activation. So we see this a bunch of times. We keep using the same dimensions as if this was CFAR10, since this is 32 times 32 times 3, and these are the 10 classes in CFAR10. So that's where those numbers come from. So that we take an image, we transform it into 10 scores. Fully connected layer. One of the ways to think about this, and this is important when we think about, like, as we're going to start looking at convolutional layers, is that each one of these rows is acting kind of like a filter, right, for that class. And so, the dot product of each of these rows is something about how aligned the image is with that class representative vector in the weights. And remember, we visualized those. Remember, we took this vector of 30, each of the rows here, 3072, length 3072, and then reformed it to a 32 by 32 by 3 image, and then we visualized it, and then, we have those kind of fuzzy cars and two-headed horses and things like that. That gives you some kind of idea of, like, what the optimization found best for those parameters to do the task. And that's what, so that's what's coming out here is these dot products. This is the dot product with the first row, the input with the first row, and then this would be the second row, and so forth. And so this idea of, like, input, dot product, single scalar output, and we do that over and over again to give you all of this is the important concept to carry over into into convolutional layers. So convolutional layers, what does it look like? Well, we're not going to. So the whole point of this is to create an inductive bias that respects the statistics, or like the correlations one would expect in an image. Okay? And what do I mean by that? Well, something like, what we can understand an image by understanding, small connected portions of the image, and putting all that information together, right? Like, we expect there to be certain kinds of correlations among pixels that are nearby each other. They might all be of the same. Like, all the pixel values might be roughly the same. That happens a lot in images, right? Like these walls, like this is all white, right? Like this happens a lot. We expect that to be the case often, because objects are often like that. There's just kind of this continuity. Then every once in a while something really interesting happens, right? You get to the edge of something, and all of a sudden that changes, right? We go from white to this background, there's some shadowing and things like that. And we also want to be able to capture that, right? We want to be able to capture that, things like in this small region of the image, everything's just kind of the same. Or in this small region of the image, there's actually an edge, and the edge is oriented, this way or that way or this way or whatever. And these are kind of like the little bits of information that that one can then, you know, characterize and then sort of continue to integrate up into higher and higher levels of integration to give you some notion of like, here's the whole of the image. So the inductive bias that we're going to build into convolutional layers and convolutional networks is that what really matters is just understanding the spatial patterns for local patches or regions of the image, and integrating that all together at higher levels of integration. And higher levels of integration means more and more layers of transformations, convolutional transformations. So we're going to start with an image. We'll still be using like the CFAR dimensions. So we still have an image that's 32 by 32 and has 3 color channels. That's the depth. So what do you do in a convolutional layer? Well, the convolutional layer is defined by the size of its filter, or its filters. So there's some typical, so you could do kind of a lot of things here, but there's some very typical ways in which one does this. One often thinks of this filter as being as deep as the image. Remember, these are weights. So like this is like W. This is like W in the fully connected layer. Okay. So so when we say 5 by 5 by 3, there's really, you know, just like here, this describes, you know, a grid of pixels. You know, each pixel having 3 intensity channels, 3 color channels. We have the same thing here, but these are going to be weights. So there's going to be, you know, a grid of 5 by 5 weights, and then, you know, sort of 3 layers of that, you know, within that filter, one for each of the channels. I mean, we typically think of these filters as being as deep as the original input, although it doesn't have to be that way. And we'll look at that a little bit, but in general, that's what it is. And then you pick some sort of small size. Again, the inductive bias being, we just need to be able to kind of characterize what's happening, you know, locally in these local regions all around the image. And so 5 by 5 is reasonable. The reason we typically have odd numbered lengths for the sides and heights of the filter is that conveniently has like gives us like a middle kind of pixel here. So think about like where this is centered. If we didn't have that, we wouldn't kind of have that anchoring. So it's just kind of convenient. Math works out nicely as a result. But it could be 3 by 3, you know, it could be 7 by 7, it could be 11 by 11. Remember, the larger that filter gets, the more and more this starts to look like actually a fully connected layer. And the smaller this gets, the more this, you know, looks like something quite different, like a convolutional layer. In fact, it's very common these days to have many 1 by 1 filters as well. Okay, so what we're going to do now is, so how many parameters would be here in this filter? How many entries in our W for this filter?
75.
Good, yeah, 5 times 5 times 3. It's going to be 75. You can kind of think of them, you know, how they'd be arranged in grids. So 3 grids of 5 by 5, right? And literally all we're going to do is we're going to, you know, we're going to slide this all around the image. We're going to like stick it on the image. There's going to be an alignment between a 5 by 5 by 3 patch here and this filter. And we're going to do this, like, conceptually, this dot product where, you know, once we do that alignment, all the entry-wise, you know, weights and inputs, we're just going to do that product. And then we're going to add all those products together. That gives us one number. That is the output of that, you know, this convolutional operation, but just for that one arrangement of the filter. And then we're going to slide the filter over. You know, in general, we can slide it over however many pixels we want to, but in general, you know, like, but conceptually, as we're learning, we're just thinking about sliding it over 1 pixel. Do that again. Slide it over another pixel. Do it again. Sorry, I've said these things many times. And what we'll get is an output layer. These things can also have a bias, just like what we had before with our linear layers. There can be a constant value associated with it. Often there is. So we talked about for a 5 by 5 by 3 filter, if we have a bias term, there's going to be one more parameter to keep track of. So 5 times 5 times 5 times 3 is 75, plus one bias constant to learn for this offset. So you get 76. So yeah, that's what this is. So this again is a linear operation because it's just a dot product, and we're just and we may or may not add a bias term here. So it is a linear operation, but we're just gonna do this. We're gonna do this kind of sliding operation, and here's what I mean. So if I take this 5 by 5 by 3, and I start it here in the upper corner, and I get one number, that number is going to fill this corner here in whatever the output tensor is going to be. And when I slide to the right, I'll now get another one here. But if I were to slide down into the operation, I get another one here. And I do this until I go from the left corner to the right corner, and start over here, one pixel down, left to right, until I get down to the bottom. And it turns out for a 5 by 5 filter that if I do it in this way, where the filter is always kind of inside the image, then what I'm left with after I do all those operations, I've basically done that like that dot product 28 by 28 times, right? There is actually 28. And I can slide this from the left to the right 28 times, each time giving me a value, and I could have slid it down 28 times, each time giving me a value. And then this is a 1 here because I just got a single scalar for every time I did that operation. Making sense? Pretty simple, right? What's cool about it is it's still a linear operation, right? So we're still being true to this whole story of neural networks are about linear operations with some nonlinear activations in between. So this is just introducing what is called an inductive bias that respects something about how we expect spatial data to behave. Cool. Now, we're not limited to just one filter per layer. We could have as many filters as we want, actually. And the number of filters that we choose to learn will give us the depth of the output here. These feature maps, sometimes called activation maps, most often called feature maps, will give us the depth. So for each filter, we can learn as many filters as we want, but each one of these filters that we learn at this layer will give us an additional 28 by 28 output in this case. So if we have 2 layers, we're going to have the feature map will be a 28 by 28 by 2. If we have 10 of these filters, we're going to have the feature map will be 28 by 28 by 10. So the number of filters for each convolutional layer gives us the size of the depth of the output tensor, which we often call a feature map. Questions about that? See, look at that. I can get 6. That's kind of cool. Like I can have this be really, really deep. Obviously, every time I do this, I'm adding to the number of parameters I have to learn. But I'm always every time I'm doing this, it's always this convolutional operation with this inductive bias. Okay, so what do these things look like, right? So we have this input. We use 6. If we have this input, these CFAR inputs, that are 32 by 32 by 3. If we have our first convolutional layer has 6 5 by 5 filters, we often just drop this number when we're talking about this because we just expect this to be as deep as the depth of the input. And if we give that number, oftentimes it's because we're doing something different than just having these filters be as deep as the input. But so if we choose 6 of these, then what we've done is this linear transformation from 32 by 32 by 3 to 28 by 28 by 6. And then we can apply our nonlinearity. So we can apply like a Ray loop, which is often an activation that's used, and that would be applied entry-wise to each of the entries in here, right? So if the entry here that's like in the 10 by 11 by third spot is negative, then we would set it to 0, and if it was positive, we'd set it would just remain itself.
What are the different filters look like? Are they different W matrices that were trained differently?
I mean, they're not trained differently. They're all trained in the same way.
So then, what kind of separates them from?
Yeah, why do they become different from each other? Yeah, that is a great question. I'll address it later again, but the short answer is those things will become different from each other if having different filters helps you to ultimately perform the task. Because remember, what's happening is we're gonna do all kinds of layers like this, and then eventually, if this is a classification task, there's eventually going to be 10 scores, and those 10 scores will now feed into a loss function, and we're going to do back propagation. We're going to update the weights. The weights in this case will be the entries in the filter, and if it's advantageous that these filters are all different from each other to do better and to reduce the loss, then that's what will happen, right? So it's driven by the task. So you can imagine like having a fairly simple task and having like a huge network. Like for some reason you chose 1,024 filters here, and at that point you might expect to see some redundancy or something like that because there's not enough signal to separate those things. But in general, this is kind of like the balance that you learn to do when doing deep learning, to learn where the capacity in your network is to learn, and make sure that it's that you're not overfitting, that you're not underfitting, that you've got something that can learn to do the task on your data set. Yeah.
Thank you.
Yeah. Good question. Yeah.
Sorry to go back a little bit, but
that's right.
So when you mentioned sliding the filter basically around, are we talking about like a shift by like 1 pixel?
Yeah. So in general, think of a shift by 1 pixel, like to the right or down or whatever. Like think of this as like, this is like a template, and there's a whole bunch of places where you could set this template.
Right. So it's doing all possible places.
Yeah. Now we'll talk about just a second. There'll be a slide on it, but the distance, like how many pixels you go in when you slide, is something called the stride of the layer. So it's often 1, but it could be 2, it could be 3.
Is that like one of the parameters?
It's again one of the hyperparameters of your network. Yeah, and you'd have that for each of your layers.
Perfect.
So all of a sudden you see, like really quickly in a deep convolutional network, there'd be a lot of hyperparameters to choose from, and often you sort of like simplify this by just making a choice for everything. And the history of like convolutional network kind of shows you like what happens when you get really specific about these kinds of things, and then what happens when you don't. And oftentimes you get the same results.
Right.
Just maybe something needs to be deeper or not. And it's one of those, it's one of these really interesting things about deep learning, is that there's a lot of choices for like hyperparameters, like the architectures. Too many choices for us to like literally do a kind of like cross-validation thing. So oftentimes we just have like heuristics that we use that just like this type of network works really, really well. Most all those hyperparameter choices will have been made, and you're just really optimizing things like the learning rate and the batch size and maybe a few other things like regularization.
So what you're saying is that certain hyperparameters are just kind of like they're just always the way they are.
Yeah, like we just we'll talk about like the family of res nets, so residual networks. Talk about the family of efficient nets, things like that. Like typically all these choices, most of these choices are just made, and you're really just about like tuning the learning rate for your data set. I mean, there's a couple other things too, like regularization for your data set really matters, but this is sort of in some sense independent of the architecture. Yeah, and there are cool kinds of layers that help make this the case. Like we'll talk about normalization layers in particular, like batch normalization, which really allow you to kind of allow this to happen. Yeah. Or when I say happen, I mean like allow this to be the case that you can sort of have a fixed architecture, like have most of the hyperparameters be fixed and take it to a new problem and have it work.
Right.
Cool, good, those are great questions. All right, yes, so we can just keep doing this, just keep on going. When we get to the next layer here, we might choose again 5 by 5 filters, and we might have a different number. Maybe now we have 10 for some reason. But again, it's very typical that the depth of the filter matches the depth of the input. And since we used 6 filters in the previous convolutional layer, that gave us an output feature map that had a depth of 6. And so our filters for the next convolutional layer need to have that same depth, so that there's, there are parameters for all of the pixels, in this case kind of abstract pixels in the feature map. And you can imagine, you can just keep doing this. No problem. Now cool, so good. So what happens here? Well, you can start to think about the what is the information content of these of these filters. So VGG is a kind of convolutional architecture that we haven't defined yet, but we will. It's actually one of the simpler ones. And this is the first convolutional layer. So what this is showing you, remember, like the first filters will have a depth of 3 because that's matching the input. So you can think of those as color channels as well. So you can visualize these, right? You can visualize these as if they were RGB images, and that's what this is right here. These are 5 by 5. I believe that's right. 5 by 5 by 3 colors. This is all of the 64 filters for the first convolutional layer in a VGG 16, which means like total depth of 16 network, which is kind of cool. So what are you seeing here? What are you seeing here? Well, so some of the things that you see here are like solid colors, basically. Actually, a lot of them they're not totally solid colors, but they're mostly solid colors. So you have some different shades of yellow, some different shades of red, different shades of like magenta. There's a cyan. There's like a indigo, maybe, I don't know. So what does this mean again? Well, what this means is, if I have this filter, let's just take this filter right here. What color do you think this is? Sometimes I don't even know how to call the colors. I didn't do very well in kindergarten. But it's kind of this deep blue or something. So what does that mean? As this thing is roaming around, this filter is roaming around the input image, it's doing all these dot products. So if we get a very positive dot product, what has to be true about the input image in that where I just did that, where I just laid that filter?
Very close to blue.
Yeah, it's going to look a lot like this filter itself. That's what a dot product is telling you. It's like the larger that dot product is, the more aligned these two things are. If these were normalized vectors, that's literally the cosine of the angle between that they're making as vectors. When they're not normalized, then it's the cosine times the magnitudes of the two vectors that you're doing a dot product with. So it's proportional to that. But yeah, in general, large dot products mean that it's aligned. So it's basically telling you, hey, you've got a blue block here, or something very close to a blue block here. What if it was like really negative? Sorry, you have a question?
Oh, no, go for it.
Okay, what if it's really negative? What would that tell you? Yeah, the opposite direction of blue, which is what? Oh no, actually, it's negative blue. Yeah, I mean it's going to be a solid color in the opposite direction. So actually don't know what it would be, but it's telling you something about, again, like it's related to blueness, but it's pointed in the opposite direction. That's information, So that's going to be true for like all these kind of more solid color ones. What about these ones where you see like patterns of white and black? What do you think about those? What's happening there? Edges, yeah. Yeah. Notice how most of them are white and black. They're not all that way. Like there are kind of these arrangements that, like this one here has got like white and it's like a mix of this magenta and black. I don't know. But like in general, you see these that you see white and black. Okay, so they're edges, and notice how many like different patterns of this we have. We have some that are horizontal, that are kind of horizontal. Is there one that's like truly horizontal? I don't think there's one that's like exactly horizontal, but you know, these, like this one's pretty close. Anyways, so again, if there's an edge in the image, and we do a dot product here, it's going to if it's you know, horizontal edge, kind of oriented in that correct way, then it is going to give you a large dot product. And again, that's an indicator that's saying like, hey, there's an edgy thing happening over here, right? And you know, there's vertical ones, there's diagonal ones, there's kind of curved ones, and all of these are, you know, they're filters. They're ways of saying you have a this kind of thing here, or you don't. Now, what if the dot product is 0? Or close to 0. What does that mean? When you have a 0 dot product, what does that typically mean? Someone's saying it, but yeah, perpendicular, orthogonal. Yeah, so like if we're thinking about these as like vectors in a certain, you know, size space, 5 by 5 by 3, so 75 dimensional space, it's orthogonal. So that usually means that they don't have anything in common, right? Like in this geometry that we've learned, like these things are not. They're not common. This is actually really useful, right? It's like if it's very large or very, you know, very positive or very negative, it's saying you look like a thing or like the opposite of this thing. And otherwise, if it's 0, it's like, yeah, you don't look like this thing at all. And so what happens when you take like, you know, a filter that looks like this, that's got horizontal edges, a horizontal edge detector, and then a vertical edge detector? What do you expect to be the dot product there?
0.
Probably going to be something 0 or small, right? I mean, it kind of depends on the exact values, but yeah, because those two things are very different from each other. And if you did the dot product, you could see there'd be like 16 squares now, something like that, or 25 of them, and you know, like they'd be patterns of like positive and negative, and you know, so forth, and they would kind of just cancel out, you know, when you do this whole thing. So that's what's happening here. Is like in this very first filter, this is what was learned. And remember, like, you actually might have thought to do this. I'm going to get you a question in just a second. But you might have thought to do this on your own. Actually, things like this have a name. They're called Gabor filters, like in kind of standard computer vision. But this is what the network actually learned when it was learning to do its classification task, that these filters ought to do that. Yeah, question?
So I'm wondering about the significance of like the gray borders around
Yeah.
it, because I'm noticing like...
So gray borders just mean it's putting it on the same scale as the rest of these things. The gray borders are literally just like, this is not part of the filter.
So why it looks like there are different shades of gray, some of them, and then...
Yeah, the reason for that is so that you can tell that this is, like, you could tell that this is, like, this would be gray on gray, so you wouldn't be able to see the filter. That's why this one's black. And this one's like a lot lighter gray, or because I guess the color contrast with the yellow maybe would be harder to see. That's the whole reason. Again, here, this would be, like, if this was gray, it'd be kind of close to gray on gray, so
that's
it'd be hard to see.
thing.
It's just a way to display it. Yeah, I should have explained that earlier. Good question. It's just a way to, so you can visualize it. Yeah, the borders don't mean anything other than to help you visualize it.
Just to clarify, so each one of those is a filter in the first layer?
In the first layer,
So
yeah.
each one of those guys are going to be
Yes.
scanned across the
Yeah,
layer?
exactly. So,
Okay.
so there are 64 of these, right? 8 by 8. So each one of these is going to give you, if we kind of follow the geometry we looked at before, like 28 by 28 slice of the output or the feature map. It's like the output, and that's basically going to be the slice that is the, this is the red square slice. Everything that's red, right? And then this is going to be the horizontal edge slice, and that's literally what that's going to be. It's going to be like telling you where the edges are, or where the red things are, or the blue things, and so forth. Yeah.
Cool, thank you.
Yeah.
So there are a few up there that look extremely similar. Those would
Right.
give you redundant information, right?
They look extremely similar, but they're actually different from each other. Like they're different shades of colors. I mean, some of them are really quite close, but for some reason, you know, it was useful to have these kind of two similar like shades of the same color, or like two similar horizontal edge detectors, or so forth. So it's not truly redundant, but it is like you could probably get rid of some of these and still do pretty well on the task.
Is that ever something people do? Is like
Mhm.
afterward they get rid of those few up there?
Yeah. In fact, there's a whole industry of this called distillation, which is you learn a large network and then you kind of learn to make the predictions of that large trained network with a much smaller network, and then you put that on your mobile device or something like that. So that's called distillation.
How does this apply to like maybe just an example of like another field instead of like computer vision or I mean
Yeah. It's a great question. I mean, this is totally driven by the data set, right? The data set and the task.
Yeah.
So whatever comes out here is a function of, right, also just like the whole network itself. But it's really, like, when the network's fixed, it's the data set and it's the task, right? Because it's that optimization that depends on the data that gives you that.
So are these used typically for other applications as well, or is it just?
I mean,
mostly-
there are fewer applications of like convolutional networks, like 2x2 convolutional. Oops, I've been staying here too long. 2x2 convolutional networks, or 2x2. What am I saying? 2D filters. I'm sorry. 2D filters, other than images, but like one-dimensional convolutional networks are used all the time for certain types of input, like genomic input, like when you can think of these filters as kind of running along the like the bases in your genome or something like that, right? Or like residues in a protein. So like this, convolutional networks are used there. Turns out that like these days, I think more like transformers and things like that are used in other. But yeah, like you can definitely use this as long as that inductive bias makes sense. That what you want to do is you want to like consolidate, like learn to kind of aggregate the information of all these nearby pieces of data.
Right, like audio or something. Maybe.
Yeah. So like audio, so another one of the examples of like using actually 2D convolution is to change your audio into like a spectrogram, and then do this very thing. Yeah. I think there was a question over here. Yeah.
I was wondering about the difference in filters. Is there an intuition beyond just like this is the local minimum of why the filters don't have redundancies in them? Like if one filter just introduced a really high value, why would the network try to make that filter again, I guess?
Because it would be redundant, right? So it has to do with this idea of capacity. So your network only has so much capacity. It's determined basically by like the size of it, how many weights there are. It only has so much capacity to learn to do a thing. And the optimization's job is to basically learn to do it. And so if everything were perfect, if we could get ourselves to like the global minimum of the loss, then that would be, the arrangement of the weights and all that kind of stuff would be, like what would get us to the lowest loss, like do it as well as we can with the task. And usually, if we have finite capacity, like if we don't have enough capacity to do the task, this will, in general, you're not going to see redundancy, unless something went really, really bad with the optimization, right? Like we just got really unlucky and went to a really bad local minimum. But in general, that's not going to happen, and it's going to use the capacity. When I say that, it's like there's going to be some error. We're going to backpropagate that signal and say like, hey, we're making errors, and it's going to go, oh, I know what to do about that. I'll adjust these weights, and then all of a sudden you have a better network, right? And that will tend to reduce the redundancy. Yeah. Also, we initialize our weights so that there's not repeated. Like they're all like there's random initialization, so they don't start off near each other. That's like another way like you could learn to do it. Like you could have this unfortunate learning episode, right? Would be that you start in a bad place, and you go to a local minimum that's bad. But there are ways of getting around that. One of the ways that we get around that is initializing in a good way. That puts us like, you know, the better part of the loss surface, that the local minimum that we do find is good.
Sorry, just a quick
Yeah.
follow-up. Is it technically possible to have like super overtime rise on your task
Mhm.
and with redundant primary again? Is that?
Yeah, absolutely. Yeah, absolutely. I think these are not, many people don't really take me up when I say this, because I think they want to do something far more impressive, at least what feels far more impressive. But I think actually really good end of the semester projects dig into this in a like into some of these questions in a systematic way, and like try to answer those for yourself. I think I think this can be really quite fun and interesting, and you'll learn a lot about, you know, the dynamics of learning and the choices of, you know, your inductive biases. So we do need to move on. We're actually behind, but that's fine, because these are fun to look at, right? So these are visualizations of the filters at higher layers in the network. So this would be like the way that VGG works is you have stages, and then like convolutional layers are different stages. So the third stage, the second convolutional layer, the fifth stage, the third convolutional layer, and these are like PCA projections of those filters, right? Like these are going to be really high dimensional at this point, because we have far more than 3 filters, right? We've been using large numbers of filters. So this is like taking the 3 principal components of those filters and visualizing those. And you know, in these lower layers, you might still see some kind of geometric properties you can latch onto, like lines, and they're now more like curves, right? And you see a lot more mixing of colors and things like that. And then, you know, this becomes, I mean, who knows? One of the really cool things to see is like the emergence of texture filters. At least that's what they look like, right? You see like repeat, so that's kind of what like edge detectors are like, but this is now happening at higher frequencies with respect to the size of the filter. So now, you know, now you're detecting textures of different frequencies, of different, you know, like orientation and different color patterns and things like that. It's like actually really, really cool what gets learned here. And then all that gets integrated into a couple of scores that at the end, you know, tell you what kind of what object is in this image, right? It's really quite fascinating. And yeah, this kind of reminds us of what happens in our primary visual cortex, but we won't spend much time with that. So the thing just to point out here is, why have we been calling this convolutional the whole time? Some of you like maybe come from engineering or physics or something like that, and you have seen, or math, and you've seen a convolutional operation before. And it literally is this idea of, and you can talk about these things as filters and such, but you have one function, and you know, it's typically like it's a filter. It's like picking out a kind of shape or distribution in your input, and you literally run it along, you know, whatever the dimensions are, 1 dimension, 2 dimensions. You literally kind of run it around your input, and you're doing you know, either an integration, or if you're still in discrete space, you know, multiple sums or whatever, and it even gets its own notation. This like asterisk is often used to represent a convolution. There's one. So anyways, we're reminded of the actual like defined convolutional operation that you might see in math and used in engineering and such. It has one big change, and that is that when we just do this kind of overlapping, we're basically just, the indices are kind of the same. Here there's like a sort of like a flipping over of the image through these negative, the way that these negative, when these indices come in a negative way, we're just subtracting this off. And when you do that, that gives it the convolution actually nice mathematical properties. Like if you were to Fourier transform this, you get the things that should, like nice things that happen. We could have respected that here in deep learning, but we don't because it's not necessary. But anyways, there's a convolutional operation out there, and it looks kind of like that. It kind of looks like it looks like what we're doing. Okay, so typically, what do the neural networks look like that we're looking at? Well, this is one of the shallower ones that we'll consider, but we have convolutional layers, we have nonlinear activations, convolutional layers, nonlinear activations. We usually just have a whole bunch of those, and then every once in a while, especially in the older neural convolutional networks, we have these pooling operations that kind of reduce the spatial extent of the images, and we'll get into pooling in just a second. But you have these every once in a while. You kind of have this like reduction, and then you have a fully connected layer that gets you to the right, to get your data in the right shape to be scored, or to go into a loss function, and you get likelihoods of the object in your image. So this is pretty typical. And if you look at these, it's kind of cool, right? Like you have the output of convolutional layer, and then you apply the ReLU. Remember what the ReLU did. So think about what we were just saying. Large dot products mean like strong alignment with the filter, right? That filter, and then like close to 0, you're like orthogonal to that filter. So if you apply a ReLU to that, what's a ReLU doing? A ReLU is now applying this kind of secondary filter that just says just focus on the large positive values and not the negative values, right? So it's like even more emphasizing the alignment. Like what comes out of this? The non-zero entries are the strong alignment. I mean, there will be some, if there's positive, they'll still be there, but in general, this will be dominated by, the feature map will be dominated by, like the large positive values, which represent strong alignment with the filters in that layer, which is, kind of makes sense. Kind of, it's like easy to kind of reason about it, I guess. I think what we're going to do in 5 minutes. Yeah, we'll just go through this and we'll just get as far as we can. So let's think a little bit more about this like sliding operation. So let's assume that our input's just simple 7x7. We have a 3x3 filter. We could have as many dimensions as we want. Just imagine this happening, in all at each one of the slices for each of the layers for the dimensions determined by the depth. So what does this like sliding look like, right? It looks like this. We are literally sliding this thing along, and if we kept doing this, moving it along, to the right, start over 1 pixel down. If we have a 3x3 filter on a 7x7 image, we get a 5x5 output, right? Because if we start here up in this upper corner, there are 5 slides to the right to get to the upper left, or to the upper right corner. So we start in the upper left to get to the upper right. And same thing, start the upper left and go down. There's also 5 slides there. So we get a 5x5 output. Now how does this change as we change different parameters here, like the stride? So the stride is how many pixels you move every time you, like when you're doing this convolutional operation. So what we were looking at before was a stride 1. You just move 1 pixel. This will be stride 2. So what will the output size be here? Good, yeah, 3x3, right? Because we have, when we slide this 2 over, we're now kind of centered there, and then then the next slide we get over to the upper right corner, and then the same thing as we're going down. So 3x3. So you can see how choosing the different hyperparameters associated with the layer gives you different sized output. What if we were trying to do a slide, use a stride 3 here? What would happen? Well, we get 1 value there, right? Then we move 3. Oh, I don't have the picture right. We would move 3, and we'd be here. And then we couldn't move 3 again, at least the way this is set up, right? What's that?
So then we'd go to the next.
Yeah, so then you go down. So like, it doesn't fit. This doesn't mean that we couldn't do this, but it would be kind of weird because maybe you'd be ignoring pixels or whatever. So it's like, it doesn't really make sense. And it's kind of like a cool way that you can think of, like, there's just some cool math to help you see what will be the the size of the activation maps or the feature maps, and that is if you take the length. We're assuming everything's squared here. So if you take the length of the image, side length of the image, subtract off that the side length of the filter, divide that by the stride, and add 1. That will give you like what is the side length of the output. Kind of easy to prove to yourself if that's the case. If you did this for stride 3 in this situation, for side length 7 of the image, side length 3 of the filter, you don't get an even number there, or you don't get a whole integer there. What do we do to deal with that? This is one of the most common things that you do with neural networks, with convolutional networks, is that you conceptually pad your image, make it larger, just by adding a bunch of zeros around it. And what does that do? Well, remember, we're doing dot products. You know, at each entry you're doing dot products. So if we have whatever the weight is in the filter, we do a dot product with a 0, that's going to be a 0. That's not going to contribute to that dot product in any way, right? So there's really no harm, so to speak, in padding your image with these zeros, and then doing this convolutional operation on the padded image. So we often do 0 padding. In fact, this is like a default built into like all the code that you'll see for convolutional layers, like in PyTorch or TensorFlow or whatever. So so what's the output now? If we pad it here, so we have 7x7 image, 3x3 filter. We pad it now with a single, row or border of zeros around it. If we use the stride 1, what will be the output size? Well, what's the output size? I start here and I stride by 1. I'll go. This is 1, 2, 3, 4, 5, 6, 7. Right? So actually, in this case, it's going to preserve the size of the input. Right? It's actually going to be 7x7. And that's actually kind of nice. Like this is almost always done. I actually don't know of like examples where networks, convolutional networks that don't have the padding, but you almost always do this so that this is not one of the things you have to think about. Is like you don't get a reduction in your spatial dimensions from the convolution. Usually that preserves, like that's an operation, or that dimension or the size of the input and the output are usually maintained with a convolutional operation, and it's only through things like pooling and other kinds of like dimension reduction operations that you get a reduction in the size of the output. And it turns out that you could use your larger filter in that case. Yeah, so instead of this thing, this is what I was saying, instead of this shrinking, the output volume would remain the same, 32 by 32. Oh yeah, this was like a question you're supposed to answer, sorry. What's the number of parameters in this layer? We'll end here with this last set of questions. If we have an input volume of 32 by 32 by 3, we have 10 5 by 5 by 3 filters, and we're using a stride 1, and this time we use a padding of 2. And why do we use a padding of 2 here? Because the filters, instead of, in the example we were just looking at was 3 by 3, and so you can kind of like, when you sat that filter in the top left corner, where like the center of the filter was on the top left corner, the 3 by 3 it only extended beyond the image, 1 pixel on either side. But if you have now a 5 by 5, it can extend 2 pixels on either side. So the 0 padding of 2 allows you to have the filter be centered on the extremities of the image. So, what's the number of parameters in this layer? Yeah, what's the very close. We just forgot the bias. Yeah, good. It's the same as before. Even though we have the padding, the filter sizes are the same. We're just now running it along like more of the image to give us larger output, but the number of parameters stays the same. I think we made it. So there's this slide that you can go look at and has all the math of the things that we looked at today for like determining, given the parameters of your convolutional layer and the input size, what the output size will be. All right, we'll stop there. I'm going to stick around. I'm happy to answer questions.